All right, so first, Nat, can you just confirm that you're okay with us recording this for later distribution?
Yes, I confirmed that I'm okay with being recorded for distribution.
Thanks. So welcome, everyone. Thank you so much for coming to the first in what we plan to be a series of webinars on sort of useful introductory, late undergrad, early grad level material relevant to folks doing plasma physics, space science sort of work. Um, This one in particular is motivated by some work from the Chimeras working group under the MagNetUS umbrella. And that group is working on the design of what we hope will be a new laboratory experiment to access a regime that is simultaneously collisionless, high beta, and magnetized. And we're interested in seeing how machine learning can work with some of our goals there. Realize that maybe we are not experts on the material ourselves, and ask Nat to come in and tell us about machine learning so we can be more informed in that. Uh, so this is Dr. Nat Mathews, who is an applied mathematician focusing on inverse problems and machine learning. They completed their bachelor's at the Rochester Institute of Technology in 2015 and their doctoral work at CU Boulder in 2021, and have spent most of the last 3 years as a postdoctoral researcher in the NASA postdoctoral program at NASA Goddard. Now they work as a research scientist at the University of Maryland and continue to collaborate with folks at Goddard and beyond on a variety of space and plasma physics problems where their expertise can be of help. So we're thrilled to have them here with us today to kick off this seminar series and teach all of us a bit about the foundations of machine learning. So with that, Nat, it's all yours.
Great. Thank you so much. I'm so excited about this. Let me share my screen and then you all see. Okay. Is this visible? Okay.
Yes, it's
thank you. Great. Thank you again so much for having me. And I'm very excited to talk to you guys about machine learning for physicists like us. I'm secretly a mathematician, but I pretend to be a physicist for work. There's a bunch of people who help with this. Most of them didn't know it, but there are so many tutorials and code examples and things like that for machine learning around that I have used to learn myself and scrounged for refactoring for examples for you guys. So first of all, here's a brief outline for the talk that I'm going to give today. We're going to talk about some fundamental building blocks of machine learning, what it is, how it works, why we use it, and how it functions. We're going to talk about a specific kind of machine learning called an autoencoder, just as an example of something a little bit more complicated. And then we're going to talk about physics-informed neural networks at the end, which are a more modern class of machine learning that's really useful for the kinds of problems that we work on in the field. The talk is actually going to look a little bit more like this. I've prepared little tutorials, code example notebooks that you can download and run yourself that I will also download and run here now live. So hopefully they work. And ideally, this is a little bit more interactive. And finally, the talk, there's a chance that it looks more like this because this is a lot to cover. And ideally, we get to everything, but I might not get to everything. So we're going to try. We're going to see how we do. So like I said, you can follow along, but this is not a workshop. There are sometimes SunPy especially does this a lot, but there are communities that run workshops where people come in and they sit there for a couple of hours and we sort of debug everything. And you're like, my Python environment isn't compiling. And I'm like, let's find out why that is. I'm not going to do that. So please, when I'm talking about the machine learning, feel free to stop me and ask to understand what's happening. But if your machine doesn't execute the notebooks, I will help you in the future. Send me an email later. One thing about this is that if you, I did want to ask, who here has never coded in Python before in their lives? Please raise your hand on Zoom if you have never if you've never used Python before in your entire life. Okay. Some people. It seems like not most people. Most people have at least done some Python coding, maybe for Plasma Pi or something like this. But there's some Python total noobs here, and we will do our best to talk about this in a more general way. I really like Python because it's so interpretable. It's very much like pseudocode. There is a tool called Anaconda or Conda, which downloads Python packages automatically. So you can just sort of have a little environment file and you run Conda on that environment file and it downloads the right version of Python and all the right community packages that I'm using for the examples so that you can set up the whole environment without worrying about like finding all the weird little sub packages that I'm using. The environment.yml file is in the GitHub. So that should be pretty easy to set up. If you're interested in following along now, I recommend you do that right away because Torch can take like 5 or 10 minutes to download. And you don't want to wait to be doing that when you're trying to run it. Okay. So, first of all, what is AI? I don't really love this term. So I'm going to use machine learning. So what is machine learning? It's a big question. There's a lot of sub-questions to that, like what is a neural network? You see that term thrown around everywhere, so maybe we should start there. What is this talk even about? What is Nat talking about? So machine learning, I think of it like this. It's a box, right? And the box takes stuff in and it produces a result. And you can see that there's some knobs on the box, like little tuning knobs that we can adjust, right? And you adjust the tuning knobs to different places, and the stuff you put in produces different results. And the stuff is, for us, usually things like data. This could be remote sensing or in situ data from spacecraft observations. It could be simulation. It could be experimental data from a laboratory. People do machine learning all the time with more abstract dimensional spaces like raw English text or symbolic equations, and they have machine learning for that. There's a ton of different kinds of input you can take, very heterogeneous input. And the result is usually either some kind of regression, you're trying to fit data, or you're trying to classify populations of data, or you're trying to predict and extrapolate, you're trying to quantify something that's a little bit more abstracted. So there's a lot of different kinds of things machine learning models can do. Something that I think we run into a lot as physicists is that we build our science question and then we figure out the way we would solve that normally, and we just say, can we swap some pieces out of this with machine learning? But machine learning can do a lot. It does everything approximately. So that's the give and take. But if we've built a machine learning model, if you're coming in to just execute something, you download something off the internet to use, this is what it looks like. But we're going to make machine learning models today, and there's another step to doing that, and it's called training. So when you're training, there's this additional step where you compute how wrong the result is. And then you feed that wrongness back in to the machine learning model. You tune the weights to be less wrong, basically. So this wrongness is called the loss. And it usually is either you know what the right answer is because you have a bunch of training data where you have the right result you want for that stuff, or you compare it to itself, or you know the physics. There's something you know that lets you compute how wrong you are. And then you tune the knobs on the side of the box to be less wrong, to get a result that's better. And that tuning is training. So this is the understanding of machine learning that I think is pretty common. But if we're going to build it, we have to open this box. This is not a black box. We can open it up and see what's going on inside. So inside the box is a pipeline, right? and it turns the stuff into the result, turns the input into the output. And it does that by combining the input or interstitial steps in the pipeline with the weights, the knobs on the side of the box. And it does that combination with a bunch of math, and that math is what we're going to talk about. So the rest of the talk is going to be about this pipeline and the math that we're doing. So now we can ask a question like this. What is a neural network? Okay. So if you were just trying to solve general kinds of problems, right? If you're in the 1950s and you're trying to solve general kinds of problems, you might use a model like this. This is a linear model, right? We have some input vector and it multiplies a matrix of weights. And then we have additional weights called the bias. That's a vector we add that mediate, right? We can make it inhomogeneous so that we don't have an origin intercept. So we can solve linear problems like this. But machine learning, we want to be nonlinear. So we have to make this more complicated to solve a much broader class of problems. We're going to make this much more powerful. And we're going to do that by wrapping it with a nonlinear function. Well, that's a good start, but that's very simple. We can't, sure, we have to be more complicated than this. So we wrap it with a nonlinear function, and then that's the output. That is the whole process. This is all we do. Okay, well, then the nonlinear function we're wrapping this with must be really complicated, right? It must have a lot of knobs that we can tune to capture the nonlinearity really well. No, it doesn't. The activation function is what this is called, and it's things like hyperbolic tangent, or a little sigmoid that goes from 0 to 1, or my favorite, which is just 0 until 0, 0 for all negative x, and then y equals x for positive x. These are the kinds of nonlinear functions that we're talking about. Okay. So that's a neural network, but surely we can make this more complicated. We can use this as a building block to create something called a deep neural network. Maybe you've heard of this deep learning, deep neural networks. This must be the really complicated part. How can we turn this into a deep neural network? What do we have to do? We just do it more times. We just do exactly this more times. Each neural network is going to be a layer. It's also sometimes called a dense layer or a fully connected layer because the weight matrix is dense, right? Every x input connects to every x2. And then we just take that x2 output and we use it as input for the next layer of the neural network. And then we just keep doing that a couple of times. And the more times you do it, the deeper the neural network is. That's it. So let's do it. I have an example that I'm going to run. The example, because I wanted to pick something really simple, is a canonical data set from people who do intro to machine learning a lot. It's a data set on cancer research from the University of Wisconsin. So if cancer is a difficult topic for you, you might want to come back in 5 minutes, and I promise we'll be done by then. We're not going to talk about cancer a lot, but I did want to mention.
There is also
before we do this, also Emily has her hand up. Yes.
Not about cancer, about the last slide that you had. How does could you explain again or in more detail how the nonlinear function acts on the matrix? Because I get that you're solving, just basic linear.
So basically what you do is you get your y1 element, your y2 element, your y3 element. Sorry. You get these elements, right? So you do ax plus b, and you get a bunch of elements of a vector, right? And then you operate tangent or the sigmoid or minimum absolute value in 0 on every element of the vector individually.
Oh, okay. And then that gives you, why are we
doing that?
Yeah.
because it's a nonlinear process. And we want to be able to capture nonlinear processes. So we just pick a really simple nonlinear process, and we do that at every step of the network. And you might say, but Nat, why does that generalize to fitting arbitrary nonlinear functions? And it's basically because if you do it in a deep way, you layer these one after the other, and they each handle a different small piece of the full nonlinearity.
Okay, so you can use them as like a basis to build up.
Yeah.
Okay.
So each one of these layers is a small part, right? And they build up a full nonlinearity.
Okay.
But you don't wrap them, right? It's just you do hyperbolic tangent to get x2, and then that will go into a new linear system that gets hit with its own hyperbolic tangent to build x3, and so on.
Okay, cool. Thank you.
Okay.
I think that, yeah, that answers
Great.
the level, I think.
Okay, there's another hand
right now.
Quick question. When you do these layers, are you always using the same, say, hyperbolic function or nonlinear function? Or do you rotate through, or what?
You usually pick one that works for your problem type the best, but there are cases where you use more than one, and we're going to do it in the next example. So we're about to do that. But yeah, usually you mostly do one of them. And these are the kinds of hyperparameters that you try different things and you see what works. Okay. So here's my little GitHub. I've already downloaded everything, and I've built my Conda environment. So I'm just going to run Jupyter Lab and open everything up and open this neural nets little notebook here. I'm going to restart and clear everything, which I will do for this one and the next one, but not the pins notebook because it takes a little too long to run and I want to talk about it. Actually, before I show you this, I'm going to briefly look at what we're going to do, because I got distracted by questions, which were good questions. We're going to have these population. It has 30 parameters and 2 classes. So it has a bunch of measurements and then zeros and ones for benign or malignant tumors. We're going to train a model to basically predict whether it will be in the 0 category or the 1 category based on the input parameters, the 30 input parameters for each data element. So we're going to output a scalar and then convert it back to a class at the end. So here's what the code looks like. We're going to have some imports. So these are grabbing Python libraries that we need for the data or for analysis. And then these are the imports that handle the machine learning packages we're using. There's 2 parts here. There's a backend and a wrapper. So Torch is doing the actual machine learning. There are 2 big machine learning package environments in Python. There's Torch, PyTorch, and TensorFlow. We're using Torch. It's a little bit more community supported. There's more open source packages for it. It's updated more frequently. And I find that it plays better with different systems. So we're going to use Torch, but you will see people use TensorFlow. Also, it does all the same things. Keras is a wrapper that sits on top of it. And we're going to use Keras for most of our calls because it greatly simplifies things. It handles a lot of the nitty-gritty details of under the hood machine learning so that we can just take the big picture and see what's happening. We're going to load the data set, and we're going to split off some data for testing and train with most of it. And then we're going to build our machine learning model. That's this part right here in the middle. So you can see I'm calling this thing called Keras sequential. That's just building a multiple layer machine learning model. And each one of those layers is here. The first layer is the input layer, right? That just takes in all the information. There's no weights associated with that. And then I have these alternating dense layers, which are the neural networks from before. and what's called a dropout layer. And a dropout layer just takes some of the weights and randomly throws them away. Some of the outputs and randomly throws them away. Why would you want to do that? We only do it when we're training, and it's to minimize the amount of overfitting that we're doing. If the neural network is constantly losing some small percentage of its own outputs, then it won't put too many eggs in any one basket and fit the data too precisely with wild weights that are unrealistic. So we are telling the network to be more robust. And when it's actually running in practice, those dropout layers won't do anything. You'll notice that I'm using hyperbolic tangent for most of the activation functions and sigmoid at the end. Why am I doing that? Because we were just talking about this. It's because sigmoid maps things from 0 to 1. And our classes are 0 or 1. So that's a really nice property. Finally, we compile the model. We're using something called binary cross entropy as the loss function. This is just a loss that works really well for data classification. And then we will train it. That's what this model.fit command does, is it's running all of the training with the data that we're using. And then at the end, we're going to get an output which is between 0 and 1, but it's not 0 or 1. It's a scalar value. It'll be like 0.8 or something. And then we split that into zeros and ones like the original data set by just saying if it's above 0.5, it's a 1. If it's below 0.5, it's a 0. So we're going to go look at the notebook. Now there's a question also.
Yes, just one quick question, because I'm as dumb as anybody in this. If you go back one slide, so how do you know, or the rates that you have, like say the rate is 0.2 or the layer dense is 12. So these numbers, is this from your experience, or is this like, are we following some rules on laws? Not laws, but some rules that we have to or is this just like you have done it so you know it, and you are giving this just as an example? Like if I don't know anything, would I just try it out, or?
Yeah, you just try it out. You just play around with it. These are called hyperparameters, and usually you tune them to get results that are decent with validation data.
Cool.
We're going to talk a little bit about the difference between validation and testing in just a moment when I look at the notebook. But in general, you just tune them out. It's important to note that we start with something with 30 because that's how many inputs we have, and we end with something with 1 because that's the expected output. And I've just had these different layers that are like trickling down from 30 to 1 over time. The more weights you have, the more precise you can be, the more complicated an action it will do. But you need more training data to fit all those weights. We have like 500 training elements, so I didn't want a huge network. Okay, so let's run this. Here's the imports. Shift enter. If you've never used Jupyter before, shift enter runs a cell. And then after everything is imported, we can look at some of our data. So I import the data and I split most of it off for training. And then some of it at the end, basically the last 10 elements of the data set, I'm going to set aside for testing, and I'm not going to look at them until the end. So you can see here are the names of all of the dimensions. I just think of it as an abstract 30-dimensional space, but these have real things to them. They're things like texture and perimeter. And then the labels 0 is malignant and 1 is benign. Okay. We build our training model using binary cross entropy, and the optimizer we're using is called Atom. This is the thing that looks at the loss and tunes the weights to minimize the loss, right? It's like a gradient descent type algorithm to do this minimization of this surface. Because it has 30, the surface is a function of 30 dimensions and it produces a scalar. So we minimize that. You can use stochastic gradient descent. There's a bunch of things you can use. We're using Atom. Most machine learning, you start with Atom because it's fast and it's pretty good. Here's the keras model that we built. And you can see that it has about 900 parameters to fit. And we're going to use what's called a validation split of 0.1. That means that we take the training data, right? I already set aside 10% of it for testing. I'm already not thinking about that. But of the training data, we set aside another 10% of it. And we say that this is for validation. I'm not going to train on it. I'm just going to look at how the errors. So this is how we do those hyperparameter fitting. A lot of the time when I'm trying to figure out how many layers I'm using, I'm looking at how I'm performing on validation data. It's important to not use the testing data for this, right? Because you could contaminate your results. You don't want to train on it, even in just a hyperparameters way. But the validation data is like a proxy. It tells you about how well you expect to do on testing data. So we run the fit. You can see it's really fast because this is kind of a toy example. And we're running up to 100 epochs. There we go. And finally, we predict. So now we'll look at the training data and see how well we did. I can see there's a couple hands up. But let me just finish this thought, and then we can get to it. So here is the training data. And like I said, machine learning at the beginning is a fast approximator. It's not going to get everything right. Here, I've plotted just the first 2 dimensions of the 30-dimensional input. And here's our 2 populations. So you can see that mostly one population was over here and the other one over here, but there's some overlap. And then here in the lower panel, we've plotted all of the ones we got wrong from among the training data. And you can see we're mostly in the middle. And a lot of them aren't all pink or all teal. They're in the middle somewhere. So they're closer to 0.5 in value. Because remember, we predict a scalar and then convert it to an integer. And then finally, let's look at the testing data, which we still haven't looked at until this very moment. And we can see that we got 9 out of 10 of them correct. Yeah, there's a couple questions. Jimmy, what's up?
So the epoch here is basically how many times you go through the data set, right? Like how
training data. Yeah.
I noticed that kind of as I did this myself, the binary accuracy like kind of bounces around past a certain point. So could you say a little bit more about kind of how you think about the number of epochs that you should be doing? Like basically how much should you go through the training set? Or like if I was thinking about this visually, like is the loss function, it just kind of like converged to something and then it just basically bounced around a particular value? Like what's actually happening here as I sort of go through this data multiple times?
Yeah. So what happens is exactly that. The loss function converges to a value and then kind of bounces around, either as the weights sort of converge and stop changing very much, or the minimum is very steep, and these optimizers like bouncing back and forth at the rim of it. And sometimes it's hard to tell which one of those things is happening. Basically, when you're looking at something like this, if your training is expensive, here it was very cheap, so we just did 100. If your training is expensive, you can try to do fewer and see like when the losses really started converging, you just cut it off. A lot of the time, the loss for the training data will converge quickly and the validation loss will be a lot slower. That tells you that you probably have too many weights and it's like overfitting the training data. Another thing that can happen is that you change the details of your optimizer. Adam has a thing called the learning rate. Higher learning rates means that it will try to go further each step so it can converge faster, but end up at a higher value, whereas slower learning rates give you sort of a shallower slope that keeps going down and down and down. So it's really just something you play around with. You can also cache out early, which is something we're going to do in a later notebook.
But to clarify, the fit that you did each instance of that was what you showed earlier with we're just doing, the nonlinear fit repeatedly, or is an epoch you had your nonlinear fit and then you put that into another nonlinear fit. That was your second epoch, and your third nonlinear fit was you did it.
So every time the model runs, it goes through every layer. Every time the model runs, it goes through every layer.
That's what I thought. Yeah. Okay.
One epoch is running the model on every piece of training data. So one epoch, you run the model 500 times for the 500 pieces of training data. Then you look at all of the loss that you got from that computation, and you compute the gradients, you do the optimizer, and you step forward with the optimizer. And you update your weights. And then you run through the whole epoch, you update your weights again. This is called batching, right? Basically, every time you take your training data and you collect it and you run a bunch of it through at once because that's faster. And then you update your weights. Then you look at the next batch of training data. You update your weights. What we're doing here is we've taken our 500 pieces of training data and we've put it in 16 buckets. And we run through a whole bucket every optimizer step. So we run through a whole bucket, we tune our weights. Next bucket, we tune our weights. Next bucket, we tune our weights. So we've tuned our weights 16 times every epoch. So we fiddled with our knobs 1,600 times in this notebook.
Okay, so it's not even there's even a further sophistication than what you showed in one of your intro slides with the linear operator and then hugged by a nonlinear operator.
Yeah, so this guy right here, right? Every training data we pass through this. This is what the model is doing. This is what's inside of this guy.
Yes.
One loop of this around the result, you compute the wrongness, you tune the knobs, right? That's a step of the optimizer.
Yes.
And you look at all of the training data and you keep doing this. And we would love to do it once for all the training data all at once, but we can't fit that on the computer. So we split the training data into buckets and we do it a few times each loop. And then we do, that's called an epoch. And then we keep doing multiple epochs to refine our model until it slows down.
I think I understand. Okay.
Mel, you had a question also.
Yes. Well, Jimmy, I had two questions, and Jimmy asked one of them, which was about what an epoch is. The other one is also, so you said that this ends up with, like, say, 900 parameters. What should I think of those parameters as? Are those the weights? Are those something else?
Those are exactly the weights. Parameter and weight are pretty indistinguishable here.
Okay.
And they are the elements of those matrices. Okay. Cool. Let's move on. Let's do a slightly more complicated model. What is an autoencoder? This is a term you see thrown around a lot. The reason why you see this a lot is because people use it a lot. And the reason why people use it a lot is because it's pretty easy. An encoder is a machine learning model that takes input and represents that input in an abstract high-dimensional space called a latent space. And then the decoder projects the latent space back into something we can understand. One example of an encoding that people are often familiar with is the Fourier transform. You take something understandable, physical wave, and you encode it in a high-dimensional abstract representation of frequencies. And then you decode back to physical space. You run the inverse Fourier transform. It turns out that this is a model that's really useful in a ton of applications where you have things that rely on spatial scale variation or temporal variation, or the input space is just really abstract, something like the English language. and you can encode words into a meaning space, some high-dimensional abstract space of like Rn. To do encoding, a lot of the time you use something called a convolutional layer. So a convolutional layer just has a window, a convolution window that passes over the input. 1D and 2D windows are both common. 2D convolutional layers are how we do a lot of image learning in machine learning. 1D convolutional layers are often for time series. And you basically just pass the window over the signal, and you add up all the window elements times signal elements. If the window is sort of a smooth Gaussian, this is a smoothing operation. But remember, this is a really powerful and general class of layer. The Fourier transform is also a convolution. It's an integral convolution, right? So we can represent things like that in this way. So we're going to build our encoders out of convolutional layers. And the little elements of what's in the convolutional window, those are the weights. And we can do this for one-dimensional input, or as the bottom GIF shows, multi-dimensional input. And we can have multiple convolutions for every given input to sort of learn multiple convolutional windows and add them together to get high-dimensional outputs. So yeah, there's a question about this.
Are these lossless processes or lossy processes, or?
These are lossy processes. So that's an encoder model. What is an autoencoder? Well, an autoencoder is what you do when you're too lazy to label all of your output data. So you just trained the input data. We're just going to train a machine learning model to project to an abstract space, a lossy abstract space, and then project back out to the input again. So we're going to look at an example using Parker Solar Probe data, so spacecraft data, where we want to do feature detection. So we're going to take our input data, we're going to train an autoencoder to project to an abstract space and then back again to reproduce the input data. And the idea is that then when it's halfway through, when it's in the abstract space, is just saying something about the time series information. Then we're going to run that autoencoder on testing data from another time interval that's a disjointed time interval from the same spacecraft, from Parker. And we're going to look for places the autoencoder does badly, doesn't reproduce the data very well. And we're going to hope that there's interesting things happening in those places. So we're going to try to detect interesting moments to look at with Parker with an autoencoder. So this example is a little bit more complicated. The data is real spacecraft data, not toy data set that people use for machine learning all the time. So we're going to have to actually process it a little bit. We're going to have to split it up into smaller time windows, right, that we sort of pass over the data set. So we're going to create sequences, overlapping sequences sort of for every time window that we're moving. We'll build a big array. And this also shows you how that batching from earlier really works. I'm going to talk about that a little bit more in this example. And then we're going to build a sequential neural network with keras again, using these 1D convolutional layers. Filters is how many different convolutions we are taking. So it's sort of the output dimension of the output vector of the layer. And the kernel size is how wide that convolution is going to be. And then at the end, we make sure that our final output is the same dimension as the input data. We're using magnetic field data, so it's three-dimensional, so we want to make sure the output is also three-dimensional. And then we're going to use atom again. So let's look at it. First, we get the Parker Solar Probe data. So I'm using CETA-Web to do that, which I don't want to talk about too much if you're unfamiliar with CETA-Web. But basically, we just download the data, and it comes in with as time series, and we make some training data, and we build our training input. So this is the first thing I really want to talk about. So if we look at how many pieces of training data we have 76,989 training times. And basically what I'm going to do is split them up into each one being a 4-hour window. And I'm just going to have a different 4-hour window with 1 minute's time steps forever. And that's going to give me a ton of them, 68,000 different windows. And I've arranged this in this shape. I built a 3-dimensional array where the first dimension is 68,000. And then these are 240 by 3 is the standard size. This part always needs to be the same for your machine learning model, because the machine learning model layer sizes aren't adaptive. It expects the same input every time. But time series can be variably length input, right? So we want to make sure that we're always taking the same size input data. So what we do is we just make sure we're only taking 4-hour windows. And this first dimension is the batch dimension. This is the dimension along which I've layered all of my training elements one after the other. So I built a big stack of them. You always put that big stack, the batch dimension, for your training data as the first dimension of your variables, in Torch, anyways. We build our sequential model the same way. It once again has, at this time, 4,000 parameters, more complicated model. And then we call our fit, and it runs through 10 epochs. Again, the batch size is 128. So we're looking at 128 different 4-hour windows. Every time we run through the model, it sort of takes those in all at once because memory can fit that many. And for 128 times 443 has got to be whatever this number was up here. I'm not going to do that math, but I believe that. This patience thing right here, patience equals 5, just means if we're not improving and we haven't improved in 5 epochs, just stop. We are using, mean squared error is our loss for this one. Yeah, Emily, you had a question.
Yeah, what's the convolution that you're using here?
So we are using the 1D convolutional filters, like in the GIF, and each one has 10 elements in it. That's what the filter size means. So it's got 10 little elements that it passes over the 4-hour window. And in the first step, I've got 32 different filters that look at all the data. And then I get this 32-dimensional vector, and then I have 8 filters that look at all of those in the next filter layer.
So the filter is essentially just a smoothing.
It if the filter is shaped with all positive sort of decreasing values like a Gaussian, then it's a smoothing operation. In general, it's just something about temporally local information talking to each other. It's a smoothing-like operation for sure.
Okay.
But we learn the details of it. The machine learning model will learn the details of it. So here we plot. Jimmy was asking about the training and validation decreasing plots. History has a dictionary of these losses in it, so we can plot them and look at them. And what we can see here is that we decrease really fast at first, and then training sort of bottoms out, validation bottoms out a little bit higher. So we'll probably have too many parameters. That might be something to look at to try and tighten up. We're probably overfitting a little bit. But we could play around with this. We could change our learning rate as well if we wanted to try and get lower values out, and so on. There's a lot of things that we can do here. We also want to look at the mean absolute error loss. So we're going to just run our model and look at how well it does on all of the data. And we can see that mostly it does pretty well. And wherever the worst it did is, that's where we're going to set our threshold. So for our testing data, if it's worse than that, we think something interesting has been happening. Here's an example of how it fits it. We can see that it's fitting it okay. Doesn't fit it super well. And now we get our testing data. We download the testing data the same way and process it the same way. We make our little 4-hour windows because even though we have a different amount of testing data than training data, we need to take the machine learning model expects the same size data. So we split it into 4-hour windows, except the batch size, the first dimension now is a different batch size. And we run our machine learning model. Model.predict runs the model on the testing data. And then we find everywhere that we did worse than the threshold that we computed before. And we think that's where interesting things are happening. So it runs pretty quick. And we can see that this time it did have some samples that were worse. And they're mostly all in this little interval right here, which is right before Parker Solar Probe crosses the heliospheric current sheet during its closest approach to the sun, which is nice. So we successfully found an interesting time. It's worth noting that this is not just like finding high amplitudes, right? Because it didn't flag these regions over here. So it's noting that something about this region is behaving in a different way than it saw during training. We didn't build this model in a super interpretable way, so it's hard to know exactly why. From a quick notebook, we could run through and sort of see in more detail. We can, now that we have these regions flagged, we can investigate them and see what's going on. But this is an example of an autoencoder. Okay. Physics-informed neural networks with 10 minutes to go. See, I knew this would happen. So we've talked about training data. Yeah, Jimmy.
Just before you get to physics-informed neural networks, so I was following along with this example, and the question I had is basically how to interpret some of these numbers. Because, for example, my training loss looked different numerically than yours did. I started at like 5 and didn't really decrease that much, but I sort of decreased to basically the same values that you had. And on some level, I know that this is non-deterministic. This is to be expected. But I didn't really immediately know what to make of the fact that so
when you initialize a machine learning model, weights are set to something. And sometimes you have an idea ahead of time of which you want the weights to be. Sometimes you want to set them all to 0. It really depends on the structure of the machine learning model. The default in keras is to set them to a random value, I think between 0 and 1. So the whole matrix is populated with random numbers between 0 and 1. And you started with different random numbers than I did. The fact that we converged to a similar actual value tells us that the optimizer successfully found a pretty global minimum.
Neat.
Okay, so we've talked about training to labeled data, supervised learning, like the classifier model we built. We've talked about training to reproduce input data. That's autoregression. And the last thing that I want to talk about in a couple of minutes is training if you know the rules. So that's a physics-informed neural network. Normally, neural networks for physics can be really expensive because making training data is hard because you have to run a bunch of experiments, or you have to send a probe into space or something like this. You run huge expensive simulations on a computer. It's difficult to get training data, and you usually don't have a lot of it. And you also really need to carpet your whole input space, because machine learning models most of them are bad at extrapolating. They're good at interpolating, they're bad at extrapolating a lot of the time. So we can solve both of these problems by putting the physical equations into the loss function. So remember this guy, the machine learning model from before? When we compute the loss, so I want to talk a little bit about how this part happens. And how we update the weights given a loss and how wrong we are. Is a thing called autodifferentiation. This is the real reason, this is what the real thing Torch, the backend, is doing under the hood. Inside of that box is this pipeline, right? This pipeline right here, we're going to zoom in and look at it. It takes the inputs, produces an output by combining them with a bunch of weights. And the important thing that Torch does is it logs the derivative of everything it did at every step. The actual line of code, whatever the derivative of that line of code is, it remembers it. And then it uses the chain rule to add them all up and get an actual derivative of the output with respect to the weights, with respect to the input. And that's how it tunes the weights. That's how the optimizer knows what the derivatives are to do its gradient descent. We can hijack this process. We can take advantage of this because those derivatives, the same derivatives, can represent physical properties. We can compute differential equations with this. So we can use these physical derivatives of the output with respect to things like where in space the node is to build up a residual for a differential equation that we know we have to satisfy. And then we can put that residual in the loss function and then let physics supervise our training for us. I have an example of this in a notebook, which I don't have time to talk about, but I encourage you to go look at it. The notebook at some point steps away from keras because keras can't do what we need it to do. We have to actually get our hands dirty in Torch a little bit. So we build our own Torch trainer that does all of the epochs and batching and stuff. So I encourage you to look at that. But I do just want to show you the final answer of it. If you're familiar with Berger's equation, you'll know that it starts with a sine wave and steepens. So here is the solution that the pin makes. And you can run this on your laptop. It's not perfect, but it's pretty good. And I encourage you to play around with it and see how to improve it. One big improvement that the paper does that I didn't do is that the optimizer that they use is different from Atom. So it's worth looking at. That's it. I'm sorry that the end is a little bit rushed, but I really appreciated all the questions that people had. So I'm really glad that we got to them. But you'll just have to learn about pins in more detail another time, unless the notebooks are really good. Maybe I wrote the notebooks super well. You have to go see. Maybe the documentation will teach you everything you need to know. But yeah, machine learning can be useful in a ton of contexts. It can do a ton of things, quick and dirty approximations, but decent approximations. And I encourage you to actually go in there and get your hands in the mud and build something, because the tools make it easier than ever to do that now. And there's really good tutorials for Python, really good tutorials for Keras and Torch and everything, because tons of people are trying to learn how to do it. And again, thank you so much for inviting me to talk to you guys about this. I really like talking about it, and I'm always happy to do that. And I'm going to be talking about it again at the Chimeras workshop about more things like the pins. Yeah, that's it.
Thank you so much, Nat. I hope you could see in the chat there are already requests for you to come do another hour just on pins and excitement for some 201 topics. So I won't pressure you about coming and doing that right now. But for those who can stay past the hour, I think, Nat, you're available if people have more questions, if I remember right. Otherwise, if folks need to run, go ahead and run. I'm going to start recording here. And thank you all for coming.